Okay, in this video, this will be the first of several examples on projectile motion problems. And what projectile motion is if you take an object and you throw it or kick it or shoot it out of a cannon, you propel it somehow or another, and it's only acted on by gravity, then you have a projectile motion problem, or what some books call a free body motion problem. Now, if you look in the book, you'll find a formula, and the formula for the object's position looks like this. So its height or its position as a function of time is given by y sub 0 plus v sub 0 t minus 16t squared. Now the components of that are this. Y sub 0 is the object's initial height, and we're going to work in feet here. The object's initial velocity is in feet per second. T is time, and where the minus 16 comes from, the general formula, it's minus 1/2 whatever the gravity is. Now on Earth, gravity is minus 32 feet per second. So half of 32 is minus 16, and that's where that coefficient comes from. Now, if you were on the moon, you would change this, and this figure would be different from the minus 16. But on Earth, minus 16 is going to work just fine. So this is the general formula for projectile motion. Now, in most of the problems, we're going to be interested in three things. The object's position, the object's velocity, and the object's acceleration. So let's look at a sample problem and see what it looks like. And the first problem is going to be pretty simple. Suppose you'd had this, that here you are standing on a cliff. The cliff's 100 feet high, and you're going to take a rock, throw it up in the air, gravity's going to take over, pull it back to the ground, and hits the ground right here. And you would like to answer several questions about this, and let's see what they look like. Now to start with, whenever you work with a projectile motion problem, first of all, you've got to set a reference height. Where is the zero height going to be? So what I'm going to do is come down here, and I like to let the reference height be the lowest height in the figure. So in my case, I'm going to let the zero height right there. That's going to be my reference height. So that's going to be 0. Now what that means is that in this case, since I'm 100 feet tall to start with, this is my initial height. So y sub 0 is going to be equal to 100 right here. Now in this problem, let's suppose this. Our initial velocity, suppose you threw this thing up at 112 feet per second. So that's your initial velocity. It goes up 112 feet per second. So now let's begin to answer some of the questions. And what we want to do is to be able to describe this object's behavior as it goes through its path. So we'll start by doing this. The first thing says, this is the general formula for position, but we want to write a specific formula for our specific problem. So in this case, I've got y as a function, and I want to change one thing here. I want to write y as a function of time is equal to, and just in place of y0 and v0, substitute your exact problem. So in our case, the initial height is 100 feet, plus the initial velocity is 112, then you've got t, then you've got the minus 16t squared. So minus 16t squared. So that is the position function for this specific problem. Now I'm going to go ahead and write it one other place here, just because as we move through the problem, make it a little bit easier to stay up with everything. So I'm also going to write it right here. So y is t is equal to 100 plus 112t minus 16t squared. So there's the position function. Okay, now the next thing I want to know is you're going to be interested in the object's velocity and its acceleration. So let's scoot down, and we'll also get the velocity function. Now, what velocity is the rate at which position is changing, or in other words, velocity is the derivative of position. So if this is the object's position, its velocity would be given by this, y prime, and just use the power rule and take the derivative of this. Well, the derivative of a constant is 0. 112t would turn into 112, and then using the power rule, the derivative of 16t squared would be 32t. So what this is a function that will give you the object's velocity at any time. So let's go ahead and write that one down as well. So we'll put the derivative y prime of a function of t, it's 112 minus 32t. So this function gives you the object's position. This new function gives you the object's velocity. Now what about acceleration? Well, acceleration is the rate that velocity is changing, so acceleration is nothing more than the derivative of velocity. So we'll go back and we'll put y, this time the second derivative of t, would be equal to, and the derivative of this function, that 112 is a constant, it'll go to 0. This will just turn into minus 32. Now, really, at this point, we could actually write down 32 feet per second squared. So what this means is, on a projectile motion problem, the acceleration is a constant, and it's just whatever the gravity is on the planet that you happen to be standing on, in this case, minus 32. So we'll go ahead and write that down too. Y, the second derivative, is acceleration, and that turns out to be a constant, minus 32. And on this one, we'll go ahead and put the units of feet per second squared. So we've got the object's position, we've got its velocity, and we've got its acceleration. We've got a function for those. Now we'll answer several questions about these, and let's see what that's going to look like. So first of all, I'm going to scoot our little graph down with this so it'll follow us as we go through this. So let's move this down to here, and we'll scoot down and look at some of the problems. So let's put this right here. Okay, now, as we go through these, some of these questions are going to involve position, some of them are going to involve velocity, and some of them are going to involve acceleration. And the rule of thumb is just this. If the question involves position, use the position equation. If it's a problem where you're interested in velocity, use the velocity equation. And finally, if it's a problem where you're interested in acceleration, use the acceleration equation. So the first problem looks like this. It says, at what time is the object 84 feet above the ground? Well, that's position. You want to know when did that happen? When was it 84 feet above the ground? Since it involves position, we'll use the position equation. In this case, you want to know when was the object 84 feet above the ground, so it'll actually look like this. You'd have set the height equal to 84 feet, and this would be 100 plus 112t minus 16t squared. So if you want to know when the object was 84 feet above the ground, just set the height equal to 84 feet and solve for t. Now, if you were to move everything over to this side, you'd have this. This would be 16t squared. Then you'd have minus 112t, and subtracting 100 from both sides would give you minus 16 is equal to 0. So move everything over to this side. Now that's just really a quadratic equation. So if you go to your calculator and use the quadratic formula or the quadratic solver in your calculator, you'll actually get two answers. And those two answers will be this. Either t is equal to 7.14 seconds, or t is equal to minus 0.14 seconds. So in this case, you actually get two answers. Now, this second answer usually confuses students a little bit. The question is, what does this minus 0.14 mean? So let's just take a look at that. So just for a second, you can do this. If you you want to know when is the object 84 feet above the ground. Well, that 84 feet above the ground, if this is 100 feet, 84 feet of the ground above the ground would be, say, about right here. That's going to be about 84 feet. So when it's 84 feet above the ground, it's right here. But from the calculator point of view, you have to remember this entire path here is really just a parabola. This function right here, minus 16t squared, is just a parabola, and it's as if this height continues on down something maybe like this. Now, if that's the case, if you came straight across from here, there's actually a second time that it would be 84 feet above the ground, but that would be almost before you threw it. So when the calculator returns this, this minus 0.14 here would be this, but in our case, this answer doesn't make any sense. So as you work these problems, if you get an answer that really doesn't make any sense, go ahead and throw it out. So in our case, we will throw out this answer right here. So I'm going to throw out this, and I'm only going to keep this answer right here. So 7.14 seconds after you throw it, this will be 84 feet above the ground. Okay, we'll go on to additional problems now. And I think you'll see, for the most part, most of these are going to be very easy to solve once you've got the initial thing. So calculus actually makes these problems easier. So we'll scoot down and look at this next one here. And we'll continue to move the figure down with us. So we'll bring it down to here. Now, what the next problem says is, when does the object reach its maximum height? Now, think about where that's going to be. The maximum height, if you actually looked at it, would be right here at the top of the parabola. Now, the idea is you throw it, and when velocity does, if you're going up, the velocity is positive. If you're going down, the velocity is negative. Well, when you initially throw it, it's thrown up at 112 feet per second. But it goes up, gravity takes over, and it begins to slow down. And just for an instant, right here at the top, the velocity is going to be 0. Then the velocity is going to become negative, and it's going to go faster and faster until it hits the ground. So the key to this, if you want to find when does the object reach its maximum height, the maximum height occurs when the velocity is 0. So what that tells you is this time you're going to use the velocity equation. So you want to know what was the time when the velocity was 0. So just set the velocity equal to 0 and solve for t. So minus 32t. So when it asks what is the maximum height, what it's really asking is at what point was the velocity 0. So now solve this, and you'd have 32t is equal to 112, or t would be equal to 112 divided by 32. And 112 divided by 32, that's going to give you 3.5 seconds. So what this means is 3.5 seconds after you threw it, it's going to hit its maximum height right there. So again, in this case, you were interested in velocity, so you use the velocity equation. Now the next question is, what is the maximum height? Well, this is a position. I think he's asking about position, so we're going to use the position equation, but what time do you put in? Well, in step 5, you found when the object hits its maximum height, so it hits its maximum height 3.5 seconds after you threw it. So to find out what the height was at that time, just take this time, plug it into the position equation, and you'll have that. So we'll evaluate the position equation at 3.5 seconds. So you know when it hit the maximum height, so that's going to be 100 plus 112 times 3.5 minus 16 times 3.5 squared. Now, if you stick that on your calculator, then the height at 3.5 seconds would be equal to, and it'll turn out to be 296 feet. So what this is the maximum height. That maximum height will occur 3.5 seconds after you threw it, and by the position equation, it will actually reach a maximum height of 296 feet. Now, just a few more general questions. Let's just kind of along that line move down, and we'll answer a couple of extra questions here. Let's scoot the figure down so that we can see what's happening here. And we'll keep this along with us. So now, what is the object's height after 1.5 seconds? Again, you want to know the height, that's position, so use the position equation. So this is just a matter of taking 1.5 seconds, plugging it into the position equation, and that'll give you the object's height. So what was the object's height after 1.5 seconds? Y at 1.5, and just in the position equation, plug in 1.5. So I've got 112 times 1.5 minus 16 times 1.5 squared. So the object's height 1.5 seconds after you've thrown it would be equal to, and this is going to give you 232 feet. Now again, at that point, it'd actually be going up because it hits this at 3.5 seconds. So 1.5 seconds, it would be about somewhere right in here going up, and its height would be 232 feet. But notice how easy calculus makes all these. You have 3 fairly simple equations, and you just pick the ones that you're interested in. Okay, the next thing says this. When does the object hit the ground? So it wants to know, when does it hit the ground here? Now, think about this. The question is, which one of these 3 equations do you use? And in this case, you'll actually use the position equation because that's all you know. When the object hits the ground, its height is going to be 0, so set the position equation equal to 0 and solve for t. So the object hits the ground when the height is equal to 0, and that's equal to 100 plus 112t minus 16t squared. Now, before you put this on a calculator, usually I'll move all these over to the other side and make this be 16t squared minus 112t minus 100 is equal to 0. Again, quadratic equation. Go ahead and put that on your calculator. And when you put it on a calculator, again, you'll come up with 2 times. You'll have a time. The first time would be 7.80 seconds. And the second time would be minus 0.80 seconds. Again, using the same argument, pick the answer that makes sense. We don't have any negative times in our problem, so we'll throw this answer out, and the object will hit the ground 7.80 seconds after you threw it. So again, the calculus makes the whole thing pretty easy. Next question says this: what is the object's velocity as it hits the ground? Now, I always get some students to do this. They'll say, well, if it hits the ground, it will stop. Its velocity would be 0. But really what the question is asking is, what is the object's velocity the instant before it hits the ground? So just before it hits the ground, how fast is it going? And again, it wants to know about velocity, so you're going to use the velocity equation. So what you want to know is, what is the object's velocity as it hits the ground? And the thing is, it hits the ground 7.8 seconds after you throw it. So to find the object's velocity before it hits the ground, take the 7.80 seconds and plug it into the velocity equation. So the velocity, y prime, would be equal to 112 minus 32. And again, you know it hits the ground at 7.80 seconds, so plug that in, and you will get the velocity the instant before it hits the ground, or the velocity as it hits the ground. And if you do that, it'll turn out to be negative 137.6 feet per second. So that's its speed just before it hits the ground. And just a reminder, if the object's going up, its velocity is positive. If it's going down, its velocity is negative. So again, it makes them pretty easy to solve. The whole trick really is just figuring out which equation to use. So let's take a look at a couple more things. We'll scoot it down here, and let's, again, move our figure back down where we can see it. So bring the figure down to here. Okay, the next thing says, actually a 2-part question. When was the object's velocity minus 75 feet per second, and how was it at that time? So the first part, again, involves velocity, so we use the velocity equation. So the question is, when is the object's velocity minus 75? Set the velocity equal to minus 75 and solve for t. So in this case, we'll put in, this will be part A. So on part A, just in place of y prime, put in minus 75. So set it equal to minus 75. That's the velocity, and we'll put that into the velocity equation. 32t. So that's going to look like that. Now, if you solve this, we'll go ahead and move this thing over. This will be 32t would be equal to, and if we move things around, this will turn out to be 187, which means that t would be equal to 187 divided by 32, and that's going to give you 5.84 seconds. So the question is, at what time was the object's velocity negative 75 feet per second, which means that it's coming down, and it reached a speed of negative 75 feet per second, 5.84 seconds after you threw it. Now we'll move to part B of the question. So you know when it hit that velocity, but the question is, how high was it at that instant? So again, it wants to know something about the object's position, so this time use the position equation. So you want to know how high was the object 5.84 seconds after you threw it. So take the 5.84, plug it into the position equation. So we'll go y at 5.84, and plug that into the position equation. So 100 plus 112 times 5.84 minus 16 times 5.84 squared. And if you stick that on a calculator, you'll find that the height at 5.84 seconds was equal to 208.4. So 208.4 feet. So it reached minus 75 feet per second 5.84 seconds after you threw it, and at that time it was 208.4 feet above the ground. And the final question, a little bit of a trick question here, what was the object's acceleration during the entire flight? Well, this is the first question that deals with acceleration. So since we're dealing with acceleration, we'll look at the acceleration function. And notice, the acceleration function doesn't have t in it anywhere, so the acceleration is actually a constant. And when you think about that, that would make sense. So the acceleration of gravity on Earth is a constant 32 feet per second. So the object's acceleration is just going to be, at any time during the flight, minus 32 feet per second squared. So really, as you work through all these problems, the thing to notice is that if you're interested in position, use the position equation. If you're interested in velocity, use the velocity equation. If you're interested in acceleration, use the acceleration equation. And you might notice as we went through this, the individual calculations are all really pretty easy. So what this was a case of standing on a cliff and throwing the object up, letting it come down and hit the ground. Now, in the next few samples, we'll vary things around a little bit. Rather than throwing it up and having it come down, we'll be standing on the ground and throwing it up and have it land on a cliff. And we'll throw some variations on those. So let's take a look at a couple more examples in the next videos.